Venturini, my apologies. And she will tell us on the formation of mini Neptunes.
Okay, so I will speak about the formation of mini Neptunes. So what are these mini Neptunes? Let's take a look at a mass radius diagram that Alona already showed one. So here we have the exoplanets with good mass radius determination, exoplanets that are low mass, so below 20 Earth masses. And here in blue dashed curve, you can see the composition of a pure water world. This means that all the exoplanets that have radius larger than this should have some hydrogen and helium to explain their low density, their extended radius. And these compositional curves just indicate, and this doesn't work, but okay, you can see that they, in principle, many exoplanets could have more than 10% of hydrogen and helium in mass. So the question is how... This one. Yeah, it works, okay, sorry. So we want to understand how to explain these objects that are very low in mass and could have more than 10% of hydrogen and helium. This is what I refer to as mini Neptunes. In the classical core accretion model, actually it's kind of difficult to explain these objects because in the classical core accretion model, all the solids go to the core. So the atmosphere is made of hydrogen and helium, and the protoplanet is able to start to bind considerable amounts of gas only when the core has around 10 Earth masses. So if we want to explain an object that has in total mass 5 Earth masses and 20% of hydrogen and helium, then it's hard to do it in the core accretion. And actually, when the core reaches this mass, it can have 10% of hydrogen and helium, but very fast it starts to accrete gas in a runaway gas fashion, so it can become a gas giant. Therefore, it's hard to, there is short time to have this intermediate range of hydrogen and helium of 20–30% in mass. But that was the classical core accretion model. In reality, the solids, it's not true that all the solids sink to the core. When the solids go through the atmosphere of the protoplanet, they get heated by gas drugs, so they get disrupted, especially the volatiles are expected to sublimate in the atmosphere. So the composition of the atmosphere changes during the growth. It gets enriched, especially with volatiles. And if we include this effect in the formation models, there are mainly two effects that happen, and it's illustrated here in this plot. This is the growth of a planet. The dashed lines indicate the case where, the classical case where everything is synced to the core, the atmosphere is just hydrogen and helium. The red is the mass of the core, and yellow is the mass of hydrogen and helium. So you see that here the crossover time, the time scale to form a gas giant, is 7 million years. But if we take into account this effect that the envelope gets enriched by the volatiles of the planetesimals or pebbles, the first effect is that the time scale to form a gas giant is reduced, at least by a factor of 2. This happens because the mean molecular weight of the atmosphere increases, so the center of gravity is more important, and therefore it starts to contract sooner, so all the process of growth occurs faster. But the second effect is that once we start to enrich, because of this increase in molecular weight, also the planet can accrete more hydrogen and helium. And there is a delay between having 20% of hydrogen and helium and reaching the onset of runaway of gas. And that's an effect on the cooling, because the opacity also increases a bit in the atmosphere. So the cooling is a bit slower. So we have some time to have a planet with low mass and 20–30% of hydrogen and helium. So in principle, this is what we need to explain these objects that are small mass and are rich in hydrogen and helium that we call mini Neptunes. This was performed in a previous work. In this case was just for a constant accretion rate of solids. So in the new work that I present here, that was just appeared in arXiv last week, so you can check it. The idea was to have more realistic accretion rates of solids, so we included a model of pebble accretion, also planetesimal accretion, and also considering very different parameters in the disk, like depending on the viscosity, as it's illustrated here, also in the comparing different conditions of the dust opacity and different locations in the disk. So here, just to summarize, a bit complicated, I don't have much time, but so it's a case for pebble accretion. Looking, each number here is the output of one simulation. The blue is when we consider enrichment in the atmosphere. The red is the classical, where everything sinks to the core. So you see, and these numbers are the likelihood of obtaining a mini Neptune. in the formation process. You see in all cases it's much higher if we include envelope enrichment than if we don't include envelope enrichment. There is a dependence on the disk viscosity because the pebble accretion depends on the turbulence of the disk. If the disk is very turbulent, then the pebbles are very extended, and therefore the embryo cannot accrete all of them, so the growth is slower. So in this case, we are left just with Mars embryos. The planet really doesn't grow if the viscosity is high. So mini-Neptune formation is favored for low viscosities and with enrichment. And then also we did simulations with planetesimal accretion. In this case, it's plot as for different distances from the star and as a function of the isolation mass. The isolation mass is the mass of solids the planet accreted at the end of phase 1 of Pollack. And the isolation mass is very high, then the gravity is very important, so it will start to accrete gas very fast. That's why in these cases, it's not likely to form a mini-Neptune. We end up with gas giants. On the contrary, if the isolation mass is very small, then the growth is all very slow, and there is no gas accretion during this lifetime. That's why also here the occurrence rate drops. Therefore, there is this sweet spot for mini-Neptune formation at these isolation masses. So I will leave you with a summary. Envelope enrichment allows protoplanets to accrete considerable amounts of hydrogen and helium before the onset of runaway of gas, due to the increase in the envelope's mean molecular weight at small planetary masses. This is what I worked on until last year. So if we include the accretion of pebbles, then mini-Neptunes are more easily formed with envelope enrichment and also high dust opacities and for low disk viscosities. For planetesimal accretion, mini-Neptune formation is possible with small bodies. If planetesimals are very large, then the accretion is very slow and there is no gas accretion during the disk lifetime. There is a sweet spot for mini-Neptune formation. It's for disks containing an initial mass of solids in this range, between 30 to 100 Earth masses. But basically, it corresponds to an accretion rate of solids in average of 10 to the minus 6 Earth masses per year. If the disks have less solids, then the planet doesn't really grow, and we are left with lunar to Earth mass embryos. And if the disk is much more massive, then it's much more easy, more likely to form gas giants. Our results favor the detection of mini-Neptunes around metal-poor stars and or low-mass disks, because we don't need too many solids, otherwise we form gas giants. And finally, as a corollary, I also found that Neptunes are very difficult to form. This is a problem. This is a standing problem in formation theories. I find maximum occurrence rates of just 10%, and for a very narrow parameter space. Some people claim that Neptunes could be formed by merging of mini-Neptunes, so in this sense, we provide seeds for this scenario to take place. Thank you, and I take questions, and I will be here a week because it's not...
Thank you very much, very interesting. Some questions?
Lunch.
Yes.
Beyond the ice line, so I take locations from 5 AU to 30 AU. The reason for that is I consider enrichment by volatiles, so by ices, and therefore inside the ice line it's not likely.
Does it matter how you form, like if 5 AU or 50 AU?
No, it matters. It changes a bit the likelihood. So for planetesimals, for example, it's better to be closer to 5 AU. For pebbles, it's better to be farther out. When you go farther out, the growth is a bit slower, so it helps. It depends when is this crossover time. If it's too soon, then here it's 0 because you form a gas giant. It's very fast to process at 5 AU. It's better at 30.
Thank you very much. Is there another question? If not, we can thank Giulia Venturini again.